All right, hello class. Welcome to case study 4A video 2. This is going to be case study 4 intro and answer. Okay, we're going to be shown case study 4 and how to answer it using the information we've gotten from our first lecture. Okay, so case study 4A, revenue from sugarcane introduction. All right, so let's just look at everything we got going on here. So it makes sense that if a farmer can harvest more acreage of sugarcane, he stands to be able to produce more sugar and increase his revenue. But statistically, if the farmer increases or decreases the amount of acreage harvested, how much revenue would be expected to be gained or lost? Okay, can data on sugarcane harvested and the subsequent amount of sugar production be used to create a statistical model? Can this model impact a farmer's decision on how much cane to harvest? Can such a model be useful in predicting revenue if one were to buy acreage for the purpose of farming? Okay, can this model be useful? Short answer, yes. Yes, if we create a good, accurate model, it can 100% be useful in helping to predict revenue for the sugarcane farmers. All right, let's read case question 4A. A farmer is considering devoting an extra 100 acres of his land to sugarcane and would like to predict the additional yearly revenue from doing so. The data available are from 14 Louisiana parishes. Records have been kept for each of these parishes regarding the amount of acreage harvested and the amount of sugarcane produced during the last year. Economic indicators are such that the prospective buyer can generate a revenue of 3 cents per pound of sugarcane produced. What increase in revenue can be expected if the farmer devotes the extra 100 acres of land to sugarcane? Okay, so that's going to be the big case question that we want to answer. What increase in revenue can be expected if the farmer devotes an extra 100 acres of land to sugarcane? Okay, so notice that's a little different than some of our other case questions. Our other case questions were surrounded around hypothesis testing. We were wanting to test a parameter. Is this more than this? Is this different than that? Okay, but now what we're doing is we're going to test to see if what increase of revenue can this farmer expect. Okay, so the data collected we see here below. All right, so we have our 14 parishes. This first variable is harvested, so that's how much sugarcane is harvested per every 100 acres. And that second variable we see is production, okay, in thousands of tons. All right, so one of the things we learned I should say we were reminded about in the algebra review is these variables x versus y. Y always depends on x, okay? So we have two variables and we need to figure out and make sure we assign them correctly. One of those variables is x, one of those is y. All right, so this first variable is talking about how much sugar is harvested, and the second variable is talking about how much sugar is produced. Okay, so which one of those, take a moment, pause, think about which one of those is going to be the independent and the dependent variable. Okay, so what we have is that production is going to depend on how much you harvest. How much sugarcane I can produce is going to be heavily dependent on how much sugarcane I harvest and gather. Okay, making harvested your X variable, and production your Y variable. Another thing to just note before we get too far into this is with these units, hundreds of acres, that's 337 acres. So that's 33,700 acres. Okay, the production in tons, all right, the production in thousands of tons, that's going to be, 940,000 tons. Okay, so we did the units in hundreds of acres and thousands of tons for simplicity because you see how it adds a lot of zeros onto these big numbers we're already dealing with. Okay. The next thing we have here is the scatter plot. Okay, so this is all the data from the 14 Louisiana parishes plotted. Okay, and I don't have a line of best fit, but I'm going to kind of just I'm gonna try to do best I can. Okay, looks like I got pretty close to hitting quite a few data points. Some of those data points lie perfectly on the line. The other ones are clustered pretty close. Okay, what do we call a relationship where we're going up and to the right and the data is very closely clustered around that line? Oop, that sentence right there. Okay, the scatter plot does display a strong positive correlation. Okay, and R will be close to 1. Okay, strong positive. Okay, strong because the dots are close to the line, positive because it's going up and to the right. Okay, so anytime we have a strong positive relationship, we know R will be close to 1. All right, so I'm going to just go ahead and go on to this new page. Okay, so this is an example of output I can get from StatCrunch. So whenever you are, this little bit of instructions right here is going to be very helpful when you are completing your homework. Okay, so open StatCrunch, click stat, click regression, click simple linear, select your X variable, select your Y variable, compute. Okay, so that's just what, that's several clicks away from getting this information that you see here. Okay, and I want to, just point out a couple things about all of this. Okay, we'll zoom in here. So here we have the line of best fit. Let me make sure everybody can read that. Okay, so this is going to be our y hat. Okay, so that makes this number our y-intercept. Okay, and that makes this number our slope. I kind of need that, so we're going to go out here a little bit. Okay, I put the hats because they're estimates. Remember, anything that we get, any numbers, numerical values that we get from StatCrunch are always going to be the statistics. They're always going to be what it is that we estimated. Okay, here we have our R value, the correlation coefficient, which we get as 0.9939. Okay, so to 4 decimal places, 0.9939. Okay, and we predicted based on this plot up above, we were like, hey, that R value should be very close to 1. And we find out that yes, it is. It is very, very close to 1. Okay, so being able to pick off beta naught hat, ooh, make sure it looks like a beta, beta 1 hat, Y hat, and R. Okay, those are going to be the 3 most important things that you want to take away from this chart. And just since we have like a lot of symbols going on, let me go ahead and separate these. Okay, 1, 2, 3, 4. All right. You want to make sure you're comfortable picking out all 3 of those estimates from this StatCrunch output. Okay, so it does give you, notice I did mention up here, it does give you the line of best fit. Okay, but in this little chart below of parameter estimates, what else can we call parameter estimates? Okay, parameter estimates is another word for statistics. Statistics estimate parameters. Okay, so here I'm gonna go ahead and change the color up just a little bit. So here we have parameter estimates, the intercept estimate and the slope estimate. Okay, so intercept estimate, that goes back to beta naught hat. Slope estimate, that goes back to beta 1 hat. And notice those are the same numbers that we got up here, okay? My slope estimate of beta 1, that's what I got right here. That's what I called that. oops, circled the wrong thing. That's what you want to be sure. Well, that's one of the things you want to be sure you're able to pick out. Okay. Now we're not really going to be using the rest of this information that it gives us. Okay. I've really highlighted right here the 4 things that you're going to want to be able to pick out from this. Okay. And again, we're not really going to be dealing with analysis of variance. Right here. These are what you want to be able to pick out from your StatCrunch output, and these little instructions that you see here at the very top are what will help you with your homework. Okay, so now using this output, I want to find the least squares regression line. Okay, so we already kind of talked about it. We found it up here, but now I just kind of want to go ahead and write a couple things out. Okay, the first 2 are the slope estimate and the intercept estimate. Okay, so beta not hat rounded to 3 decimal places, that's 12.341. Okay, beta 1 hat rounded to 3 decimal places, that's 2.848. Okay, the general form for the line of best fit is beta not hat plus beta 1 hat x. Okay, we're not going to be plugging anything in for y hat or for x. Those are what we're going to be using to help predict. Okay, so thinking back to algebra, y equals mx plus b. We're going to fill something in for m and we're going to fill something in for b, but the y is going to remain and the x is going to remain. Okay. So yeah, then what I wrote off to the side is exactly what I have written next in the notes is like, hey, well, what is that line of best fit? Y hat equals beta naught hat plus beta 1 hat x. And so all we're going to do is plug in those numbers. And now we have a linear relationship between y hat and x. Okay, and that is going to be called our line of best fit or our least squares regression line. So least squares regression line, that's the same as the line of best fit, which is the same as what we got right down there at the bottom. Okay, so the next thing that's going to be helpful for us in answering this question about the farmer is to interpret beta 1 hat. Okay, interpret beta 1 hat. So I'm going to come off to the side here. Yeah, let's go ahead. I'm going to pick purple. So beta 1 hat, this is our slope. Okay, this is m in y equals mx plus b. Okay, and this is the change in y over the change in x. Okay, that triangle delta means change in. Okay, so we want to define beta 1 in terms of the change in y over the change in x. Okay, so just a reminder that y is referring to production. Okay, and x is referring to harvested. Oh, can't do a D today, guys. Oop, there we go. Okay. Now, the other thing, the very last thing, putting it in terms of the problem that we know about beta 1 hat is that it equals 2.848. Okay, so 2.848 is talking about the change in production over the change in the harvested. Okay, so keep in mind, I'm going to be using the units from up above. Okay, talking about hundreds of acres harvested and thousands of tons produced. Okay, so the way that we are going to interpret beta 1 hat, okay, for every 100 of acres harvested, production increases by 2.848 thousand tons. Okay, one of the reasons we say increases, is because we have a positive 2.848. Okay, and that's also coming from the fact that we have a positive linear relationship going on. So we're seeing an increase in the production as we harvest more, which, we can kind of expect, it makes sense. The more you harvest, the more you're able to produce. But now what our goal is to try and put some actual numbers and some math to it for these farmers. Okay, so for every 100 acres harvested, production increases by 2.848 thousand tons. All right, and just one more time to mention that this 100 acres harvested and 1,000 tons, that is coming from the units that were given to us and upon this problem. Okay, so the next thing I want to look at is using the least squares regression line. So we're going to work on answering some questions. All right. So first thing I start off with is here is our least squares regression line actually plotted with our data now. So this is the same scatter plot you saw up above, except for now, instead of me drawing my line through it, we had Excel generate and create a line through this instead. Okay, and notice that the information we have right here is going to be exactly the same as the information that we got above from StatCrunch. Okay, so suppose a Louisiana parish contains 242 acres of land, which can be harvested for sugarcane farming. Okay, use the least squares regression line to predict the sugarcane production in that parish. Express the production in thousands of tons rounded to 3 decimal places. Okay, so this line of best fit that we have right here, this least squares regression line, okay, that's what we're going to use to predict. Okay, now the other thing to remember is that X is our independent and Y is our dependent. Okay, so Y will always depend on X. So X is what we should always be plugging into. All right, so let's make sure that's what we have. X, so here, I'll even label it down here. This is X, this is Y. So we have 242 acres of land which can be harvested. Okay, so 242, that applies with our X in hundreds of acres. So we're going to plug in 242 in for X into this linear equation that we see up here. Okay, use this least squares regression line to predict the sugarcane production in that parish. So we want to start with, hey, well, what is our least squares regression line? Okay, first I have the least squares regression line in general form. I'm actually going to zoom in real quick. This is our general form. Okay, always important to know things in the general sense. All right, and then we plug in what we know specifically, okay? What we plug in, what we got from StatCrunch, or simply looking at this y equals equation given to us by Excel, okay? And the next thing I'm gonna do is I'm gonna plug in 242 for x, okay? Now notice, once I plug in 242 for x, the only thing on the right-hand side of that equation are numbers, okay? So at this point, maybe take a moment, pause, type this in your calculator, and you should get 701.557. And the units are going to be thousands tons, okay? Because the unit that we inputted was hundreds of acres, which is what we should have, hundreds of acres. So what do we get out? Thousands of tons, okay? Thousands of tons. So if I want that in just tons, well then all I have to do is multiply this 701.557 number and multiply it by 1,000, and then I'll have my units in just tons. Okay, so that we've started to answer the question. The question is use the least squares regression line to predict the sugarcane production in that parish. Okay, we did answer the question. We were able to predict how much sugarcane would be produced if you had 242 acres of land. So the next question is, what is the revenue in dollars associated with this sugarcane production? Okay, so 2,000 pounds is in 1 ton. That's just general fact, okay? 3 cents for every pound. That was information given to us within the problem. Okay, so what is the revenue in dollars? So we know how much sugarcane will be produced. This number right here. This is how much sugarcane is going to be produced. Now, how much revenue is that going to get the farmers? Okay, so first let's convert tons to pounds. Okay, because that is what we have, 3 cents for every pound. So I need to figure out 701.557 thousand tons. Well, how many pounds is that? Okay, so we start with multiplying 701.557 thousand tons by the number 1,000. Okay, so notice in order to get from this to this, all we did was multiply this number by 1,000. Okay, essentially moving the decimal places 3 units back. Okay, so that's how many tons. So again, starting with this up here, 2,4,200 acres, this farmer created or produced 701,557 tons. Okay, next thing we need to do. All right, now we need to convert the tons to pounds, okay? And what I did right here is I used the unit conversion. So 2,000 pounds in 1 ton. That's that information right there, okay? 2,000 pounds in 1 ton, okay? And I know how many tons I had, 701,577 tons, okay? Something that we can do with unit conversions, it's like, hey, if the tons is on top here and the ton is on bottom there, they cancel out. And what unit are we left with? Just pounds, which is what we want. Okay, so what I've showed there is you're going to take your tons and you're going to multiply it by 2,000. And then we're going to end up with pounds, which is like around 1.4 billion pounds. That's crazy to think. That's a huge number, massive amount of sugar. Okay, so therefore, 701,577 tons is equal to 1,403,114,000 pounds. A lot of pounds. Okay, now that we know that, revenue can be found by multiplying the number of pounds by 0.03. Okay, we did 0.03 because now that's talking about dollars. 0.03. Okay, we converted 3 cents into dollars. All right, and then when you multiply those two numbers together, you get around 42 million. So that's what the revenue is going to be for him. For that Louisiana parish that contained 2,4,200 acres of land, the revenue will be over 42 million. All right, so that was question 1. It had 2 parts, A and B. All right, oops. Now let's do question 2. Okay, suppose a Louisiana parish contains 600 acres of land, which can be harvested for sugarcane farming. Use the least squares regression line to predict the sugarcane production in that parish. Okay, so first thing, I want to go look at our scatter plot with this number in mind, 600 acres. 600 acres. Okay, so if we look at our scatter plot, 600 doesn't even fall on this graph. 600 is going to be like out here somewhere. Okay, so 600 is going to be the x that we could plug in for y. Okay, but the actual answer to this question is that we cannot answer it. And why that is because extrapolation. Okay, we do not ever want to extrapolate. And what extrapolation is anytime we're trying to make prediction outside of our range of x values. I'm going to change the color up a little bit here. Our range of x values go from around close-ish to 0 to over 400. Okay, if we scroll back up, we can get the exact number. So this is the range of our x values right here. All right, the lowest number we have is 80, and the highest number we have is 411. Okay, so we should not be plugging in data that falls outside of that range from 80 to 411. Okay, so let me come down here and actually define extrapolation for you. Okay, so we cannot answer this question. To answer this question, we would have to extrapolate, and we do not want to do that. Okay, extrapolation is caused when we use the line of best fit to make predictions outside the range of our x values. Okay, something I like to mention about extrapolation is like, well, could we plug in 600 to our formula? Sure, we absolutely could, but it is a bad statistical practice to try and make predictions that way. Okay, we have no idea what happens outside the range of our data. Maybe there's a point where the soil, if you try to plant too much and harvest too much, the soil starts to, disintegrate or not keep its integrity. I'm not a farmer. I don't know if this is true or not, but what I know as a statistician is that I don't know what happens to that data outside of my range from 81 to 411. Okay, so I should not make predictions outside of that range. All right, and again, that's called extrapolation, using the line of best fit to make predictions outside the range of our x values. Okay, so now on to question 3. This is the last question of case study 4, and this is where we're actually going to answer our case question. So let's help out the farmer in case study 4A. What increase in revenue can be expected if the farmer devotes the extra 100 acres of land to sugarcane? Okay, so I pulled up I made a short bulleted list of things that are important for us. Okay, so for every 100 acres harvested, production increases by 2.848 thousand tons. Okay, this was our interpretation of beta 1 hat. That's going to be very helpful for us because it incorporates the 100 acres harvested, which is what we want to know. What increase in revenue can be expected if they devote an extra 100 acres? Okay, another thing that's going to be helpful for us is 2,000 pounds is equal to 1 ton, and the farmer will have a revenue of 3 cents for every pound. Okay, so I kind of just tied this first bullet in here again. The interpretation of beta 1 hat. This is where we're going to start. For every 100 acres harvested, production increases by 2.848 thousand tons. Okay, 2.848 thousand tons is 2,848 tons. Okay, that's saying the exact same thing. Because what I'm going to start with next is just another way of writing this. Production increases by 2,848 tons for every 100 acres harvested. You see how that's the same as the sentence with different units? Okay, so that's how many extra tons we'll have for every 100 acres harvested. So the next thing we're going to need is we're going to need to take this number and do what we did earlier. We need to convert it to pounds, and then we need to multiply it by 3 cents to get our revenue. Okay, so first I take 2,848, multiply it by 2,000 pounds in order to get our number in pounds. Okay, and I believe I made a note here. Okay, so production increases by 5,696,000 pounds. All right, revenue can be found by multiplying the number of pounds by 0.03. Okay, so I'm going to multiply my 5 million number by 0.03, and I land at this number as the answer to our question. Oops, got a little carried away there. So for every 100 acres harvested, revenue increases by $170,888. All right, so I started with my interpretation of beta 1 hat because it already has this 100 acres in there that I need. And I basically took this 2848 number, I converted it to tons, I converted it to pounds, I multiplied it by revenue to end up at $170,880. Okay, so that is our answer to case question 4. I'm going to go ahead and stop this video here, and I will see you on the next video.